Okay, so any questions from yesterday? No questions. Okay, did anyone try to solve that problem we were trying to do, or look at it again? No, okay. Okay, so the kind of good news is actually that problem is there is a simple solution. Okay, it's even though it looked complicated, if you just do the algebra, finally the answer is quite simple. Okay, so let me just outline what we are trying to do. So we had we were looking at a finite lattice 1 2 L, and we had a random walker. So we had random walker, and it was moving to various sites with some rate, right? So the hopping rate was r, and it's unbiased, so both hopping rates are r. And then you can write a rate equation basically. So what's the probability that it's so here space is discrete and time is continuous, and we wrote an equation for basically this object. Okay, so T, and the equation, if you are at some site like this, some bulk site, then it's quite simple. Okay, so this is some position, let's say x, and so what is the rate at which you gain probability? So this is equal to so you either come from this side or this side, so that's basically with rate r, so r p 1 plus r 1, and you lose things to the neighbors, so that's minus 2 r p of x t, right. So this is the equation, and then what we said was that this equation holds everywhere except the first and last sites, right. So at the first site, if I write the equation, the correct equation is del p 1 t. So it can only gain from site 2, and it can lose only to site 2 also, right. Okay, so now supposing I just took this equation and wrote it for x equal to 1. Okay, so then what would I get? So I would get something like del p. So if I use this, okay, this I am just writing the from the fact that there is nothing on this side, so I am just writing this equation. But supposing I just took this equation, then what is the equation I would write? So I would write this. So this term is still the same as this. Sorry? Yeah. Right side? Which one? This one? Yeah, so it's at x, it's gaining from x plus 1, x minus 1. So these are the two gain terms, and this is the loss term, right. These are the rate of loss. So no, what was your question?
My question is that I think r is rate.
Right, yeah.
Then it's fine. I think r is rate.
Okay, yeah. If it is probability, then it looks slightly different. Okay, so if I just take this and put x equal to 1, then what I get is this I would get, but then I would get this extra term r p 0, and here instead of minus 1 I would get minus 2, right. So it's minus, so let me just write it as minus r p 1 t minus r p 1 t. Right. So if I just put x equal to 1, I would get this, right. So if you compare these two, there is this additional term here, right, which I don't want. So how can I get rid of this term? I mean, the simplest thing is just to put this equal to 0, right. So that's like a boundary condition. Okay, so this basically, the fact that I want this equation but get this gives me a boundary condition. Okay, so therefore boundary condition is p of 0 equals to p of at all times is p of 1 t. Okay, so this is a boundary condition at out here. Okay, so I just imagine there is an imaginary site here, and I just put the probability same as here. Okay, So if the probability at this side is the same here, so then of course there can't be any current, right. So it's basically imposing the condition that there is no current, because the current actually, if you look at this equation, this basically tells you that at this site there is a current from here to here and there is a current from here to here, and this is just the difference of two currents. Okay, so it's like it's basically I mean like writing a discrete. I mean it's just a discrete version of this. Okay, so what is the current from here and what is the current going out? Okay, just difference of two currents, and here I don't want any current from here, so I just put the probability equal. Right, so this is just the condition of no current. Okay, and similarly I should do the same thing here, and then it's clear what I should put. So I should just put boundary condition at L is P at LT is equal to P of. Right. So I just imagine there is an extra site, but the probabilities are exactly the same, so there is no net current in this branch. Okay, so now I basically I can forget about this. I can just take this equation and I want to solve it. Right, I imagine there is two extra sites and their densities are they satisfy this boundary condition, right here. Okay, so now I will just solve this equation. I will forget about I mean this all this stuff. I will solve this with these boundary conditions. Okay, so that's the aim. Solve this equation with okay, so I think in the previous class, I mean you solved this problem where is that right? You solved this, right? Is this what you did in the right with this? Okay, so this is a problem where you have like absorbing boundary conditions, right? And you can also solve this with different. Supposing you have a box where particles can't escape, then you would solve this with boundary conditions like current is 0. So you would just say that current is given by this, right? Del P by del x. So you just say that at x equal to 0 and 0. Okay, so this is another boundary condition. You can try to solve this problem using this boundary condition. Okay, so that's what we are doing out here, but it's just the discrete version of this boundary condition. Okay. So here what you did was probably try to find some eigenstates of this operator which satisfy the boundary conditions, and in that case it's sin qx. In this case, if you do in the continuum case, it will just be cos qx, right? Because if you choose cos qx, then derivative is sin qx and it vanishes at x equal to 0 and L, right, if you choose q as n pi by L. Okay, so so now let us see how to do the discrete case. I mean we expect something close to this, right, cos q L, but yesterday we saw this does not work, but it will be something close to this. Okay. So okay, so now the other thing I said yesterday was that okay, so basically this I mean see all these things are basically they are linear equations, right. I mean so there is del p del t, and the general form is that del p del t is equal to some linear operator, right. That is the general structure, whether it is discrete, continuous. And the main idea to solve these problems is that you first solve this eigenvalue problem like Wp equals to lambda p, and then you say that any function p can be expanded in a complete like these phi's will form a complete set and because they satisfy the same boundary condition as P, so you can always expand P in this basis. Okay. So that's the main idea, that you expand this P in this basis of W, and then it's easy to solve. At least you can write this summation, and then maybe in some cases you can evaluate it exactly. Okay. So now in our case we have del P del T equal to something WP, and we have to solve this eigenvalue equation. Okay. So W phi equals to lambda phi. Okay. And we want if we write this explicitly in the component form, then this is basically the same object. So W acting on P is basically this. So W acting on phi is just the same thing, P replaced by phi, right. So this basically gives us let us say R phi. Okay. So you will get if it is a finite system, this matrix is L cross L. So you will have L eigenstates. So and I call them lambda S, phi S, is equal to okay. So these are the L eigenstates. Okay, I just label them like this, and each of these eigenstates satisfies the equation. Let us say, so that is first term is x plus 1 minus 2 R phi S x plus R x, and phi s x should satisfy this boundary condition. So this whatever wave function I find should satisfy x equal to 0, right. So 0 okay. So I just want to solve these equations with these boundary conditions. Okay. So I mean so first thing is that now see this one this one was for what Sanjeev taught in the previous class, that is called the absorbing boundaries. So the probability vanishes, right, because things are getting absorbed, so the probability vanishes at the boundary. I mean for this it's a hard box and the current vanishes at the boundary. Okay. So so this is a hard, so it's really like particles can't escape, and you want to see how the probability evolves in time. Phi see this is a see this is just some matrix, right, and phi s is an eigenvector. It has components phi s 1. So this is just the 1 2 3 means just the sides of the lattice. So this is just the vector with phi s L. Okay. And there are L such vectors. Which one? This one is the projection on the like the coordinate basis. So you are just writing the wave function in coordinate basis. Right, yeah. Okay. Right. So now how do you solve this? Okay. So first you notice that this is a linear equation. You can always try a solution of the form e to the power iqx, right, that will automatically satisfy this. Okay. But now you have to also take care of the boundary condition. So you have to take a combination. So you can take sin qx plus cos qx, or e to the power iqx plus e to the power minus iqx. You can do it either way. And then I wrote these two set of you get from this you get two equations and you have to solve it. Okay. So so if you solve it, finally actually things simplify and you get a nice answer. Okay. But let me just write the I will just write the solution, and you can see that okay. So see, first of all, you know, in the continuum case you know this answer. Okay. And see so what is cos qx? Okay. So if you plot cos qx, I mean it basically looks like, if for the smallest q it will look something like this, right. Then the next q will be maybe some function like this. Okay, so so this is the smallest q, then the next q, and so on. Okay, so all of them basically at here the derivative kind of is 0, right? In the discrete case, I mean you want something which has the same value at here and here, and similarly same value here and here, right? That's what you want. Okay, so now, and it has to be close to cos qx, right? Because you can finally take continuum limit, you should get back this. So you can try to see, I mean, so one possibility is you can just write something like this, cos q. I mean cos q L doesn't work, right? Because L equal to 0 and 1 is different. But if you write cos q, okay, I'll just, I'm using x here, cos q x minus half. Okay, this works because at x equal to 0 and x equal to 1 it has the same value, right? So this satisfies this boundary condition. Okay, so therefore I now use this and just want to satisfy this, right? So I will just put this, so that gives cos q I mean I just chose it so that it satisfies the boundary condition. And see, this is finally, if you break it up, it's a combination of cos qx and sin qx, right? So it definitely satisfies the equation, okay, and it also satisfies one of the boundary conditions, okay. So I am sure it's correct, right? So, okay, so now the other boundary condition gives this, and if I just expand this thing, what I will get is sin ql equals to 0, okay. So which means q is equal to s pi by L. So these are the allowed values of q, and I choose s equal to 0, 1 to L minus 1. Okay, so that's a complete solution. Okay, so finally you see that the wave functions are actually simple, and this is the year, and this lambda s, if you just I mean plug in the wave function here, plug e to the power iq x into this, then you get basically lambda s cos q. Okay, so also now you can take this and you can just normalize it. Okay, so it's always good to work with normalized wave functions. So this, so finally the wave functions are phi s. If you normalize it, it's the correct normalization is just this. Okay, cos. And phi 0 is a bit special. So phi 0 is just if you normalize it, it's just 1 by root L. Okay, so it's different than this normalization, so that you have to be careful. So the s equal to 0, so this is 1 to L minus 1. Phi 0 is this, and lambda 0 is just 0. Okay, so notice that all these are less than 0. Okay, so all these eigenvalues are less than 0, and this is the only eigenvalue with 0 eigenvector with 0 eigenvalue. Okay, this formula everyone is okay with? Huh? Okay. Okay, so now actually, so I had said that for like this kind of stochastic matrices, so this W is called W matrix, I mean stochastic matrix, and so one of its like usually it's not Hermitian, okay, but in our problem actually if you notice it is metric matrix, okay. So because we wrote it as this matrix this was basically minus r okay, so 1 2 3 4. So this is if L equal to 5, then this is what W looks like. Okay. Okay, so now this I mean it just happens that it's symmetric. Okay, so if but in general, like for example, if the hopping rates were asymmetric, then okay, so in that case, what would this matrix look like? Okay, so what would this element be? So supposing I have a problem where I mean this way hopping is R1 and this way hopping is R2, right? Then I would get so this is W12 means rate of transition from 2 to 1, right? So 2 to 1, so that would be R2, and this would be this is 1 to 2, rate of transition from site 1 to 2, which is R1, right? So this would look like this. Okay, and this element would have been minus R1 plus R2. Okay, and so this would all be R2s, and this guys would be R1, R1, R1. This would be minus R1 plus R2. This is R2, this is R1. Okay, so in that case it would look like this. Okay, so then of course it's not a symmetric matrix, right? So it's not a symmetric matrix, and left and right eigenvectors can be different. Okay, so if it is of this form, then like yesterday, what one property that I had said was that there is always a left eigenvector with elements all equal to 1. Right? Is that clear? Right? Even if I change this to R1, R2, even then you can check that this property. So if I write a vector like this, a left eigenvector, then you can check that because the sums are all 0. Okay, and that just implies conservation of probability. Okay, because it just says that I mean the total loss should be 0. Okay, so this is conservation of probability, and that implies there is always a left eigenvector like this. Okay. Now in this case, however, the right eigenvector is difficult to find. Okay, so if R1 equal to R2, we saw that there is something like this, which is basically this state, right? All I mean all the elements are equal. Okay, so now you can see this does not work, right? So in this case, actually, can you guess what is the what should be the eigenvector? Okay, just physically. So what does this mean? And now you have a you have a box of and you have some particles, and there's a bias. Okay, so bias means it's like a electric field, let's say, right? So if you have electric field and this vector that it's just you expect it to be the so I am asking what is the eigenvector which has 0 eigenvalue. Okay, so that should be the steady state distribution, right? So in this case, what is the steady state you expect? Will all the particles go to the right, or there will be some distribution? Huh? There should be a gradient, right? Yeah, and it's so if you have an electric field, what is actually the distribution, right? What do you expect? Huh? No, it's not linear. I mean, in gravity, is it linear? It's like gravity, exponential, right? So you expect a exponential distribution, right? So you can just try that. I mean, if you just try to the power minus alpha x. Okay, so you can actually check that this is an exact eigenvector of, because it has to be, right, because again it's a linear problem. Earlier I was saying the eigenvectors are e to the iqx, but you can also, in this case you can check that this is an exact eigenvector. Okay, and actually if you just look at it, if you just put 1 here, this has to be R1 by R2, right? Then at least the first guy is satisfied, is 0, right, because minus R1 plus R1 is 0. Okay, then the next guy, if you just put R1 by R2 square, then this is also satisfied. Okay, and the next guy is just R1 by R2 cube. and this is R1 by R2 4. Okay, so this is actually a eigenstate, and this it's clear that it's decaying exponentially, right? Just to the power n means it's decaying exponentially. Okay, so okay, so what I was trying to say is that in general this matrix need not be symmetric. In our case, it is symmetric. So actually, in our case, this phi sx and chi sx are identical. Okay, and these are all real. Right, so chi s and phi sx are identical. So here you can just put okay, this is not t. X actually I can just put phi s, phi s. Okay, so this example also, this left eigenvector and right eigenvector are not equal, right? It's clearly they are different. But in this case, both are equal. Okay, so this is the A, and now supposing I say that P of 0, so P of 0 is the initial vector, and supposing I put initially I put the particle at some point x prime. Okay, so then what does this look like, this vector? This just corresponds to the initial condition, right? So what? It's 0 0, and at x at location x prime it's 1. Right? So this is at location x prime. Everywhere else it's 0. Okay, and if I take this dot product, then what do I get? I just get phi s at x prime. Right? So if I write this vector in coordinate basis, which so x prime. Okay, and so if I just write it out explicitly, so probability it's at site x at time t is equal to, so let me take out s equal to 0 outside. So the first s equal to 0 will give me 1 by root L from here and 1 by root L from here, right. So that's 1 by L, so that's this 1 by L plus this is given by this form. So I get 2 by L sum over S T Okay, and so lambda s is given by this. Okay. Sorry. Okay, and so all the lambda s not equal to 0 are less than 0. So at long times this is going to go to 0, and it's basically going to be a uniform density with 1 by L density we expect. And then you can ask several questions. Okay, how does it spread? Okay, so how long does it take to spread to the entire box? So how long would it take, do you think? And like some estimator, how long does it take to reach equilibrium? That's the like equilibration time, right? Huh? L square by r, right? Yeah, L square by r, because r, I mean, r is kind of like the diffusion constant, right? Okay, so so tau equilibration would roughly be L square by r. right. I mean, you can put a if you just want some dimension, then you can put a like you can this is right now dimensionless, right. So this is already time, so it's fine. Okay, so this is equilibration time. So if you really look at it so this is L, and supposing you start a particle from somewhere here, okay. So if you start it from the center, then for a long time it will basically look like a Gaussian, and then at times which are greater than this, then tau let us say okay order of equilibration. Okay, then what you will see is that since this is a sum of exponentials, okay, just one term will dominate, right. So at very large times only one term in this will dominate, and you can approximate it by 1 by L plus only the smallest lambda will contribute. So it will basically look like e to the power let us say minus this guy 2r1 minus cos pi by L. Let's put 2 pi by pi. Okay, so if you actually start with supposing you start with x prime equals to L by 2. Okay, so supposing you start exactly at the center, then this term basically gives you cos minus half, and this one is non-zero only for even s, right, because supposing L is even, the number of sites is even, then this quantity is non-zero only for is not equal to 0 for s even. Okay, so for s odd it is 0. Okay, so for double dot. Okay, so let me do another thing. Let me just make a transformation, and I call x equal to okay, so because I am starting from the center, I just measure the distance from the center. Okay, so I introduce this y. So y is just the distance from the center. Okay. So I'll just put y here, and then this will just be cos qy. Okay, and this sum is now only over the even s values. Okay, so it will go to from all the way to L minus 2. Okay, so this is the thing, and if you look at very large times, what you will get is just one term, which is cos. So phi of so this is q is s pi by L, so it is 2 pi by L y. Okay, so the if you look at the probability, it will basically look like at very long times. It's going to, so supposing this is 0, so so this is the steady state value, and if you add this cosine function, where is it? So this is some cos 2 pi by L, then it looks like basically something like this. Okay. So if you look at the density profile at very long times, larger than this time it takes to see the boundary, then it will look something like this. Okay, and at short times it will just look like a Gaussian. Okay, so so I'll just give an this will be an assignment problem. Supposing you take this and okay, so and then huh. Uh, Okay, so if you do the same problem in the continuous version like diffusion equation, then you should see that the answer should be Pyt. So continue, huh? With this q is still S pi by L, but the sum is only over this, so it's still S pi by L. So okay, so if supposing you so homework is, if you look at the continuous. So verify that P of so I'll just call it Yt. So y is measured from the center. Okay, so P of Yt should be still be 1 by L. So it should still go to 1 by L, right? L is the size of the box, so it should still be go to 1 by L. To infinity. Okay, so in this case, if it's a continuous box, it should go to infinite. Okay, and so now L is just length. Okay, so it has a dimension. It is actually length, and so this goes to infinity, and this is e to the power minus. Okay, so this is you should work out this. That's one, and the second thing is you should do is if you look at it's like kind of short times, and small means basically smaller than L square by D. Then in that case you should see quite often we when you have sums like this you can convert it into an integral, right? That we do all the time. I mean, just you somehow just do this dq equal to like S by L times 1, ds is like 1. Okay, so you can kind of convert it into an integral. So in this limit, supposing and you can do this only in this limit. Okay, so you can't always, for example, if time is really large, okay, then if you look at this, okay, so why when can we convert it into integral? Okay, so if you look at this sum, so let's say as a function of s. Okay, so I am so if I look at the various objects, so let's say for s equal to 0 it is something, for s equal to 1 it's something, s equal to 2 something, and so on. Okay, and I want to make it a continuous function. Okay, now this I can do only if this is kind of smooth. Okay, but at very large times, I mean like there's one term is large, but all the terms are like it kind of decays very fast. Okay, so if time is large, then it doesn't you can't really convert it into an integral. Okay, so you can do it only in some time scale. Okay, so in some time scale you can convert it into an integral. So so that's this time scale. So you should convert this into okay, so you should if you convert it into an integral, you should show that it actually looks like this. Okay, so that's basically the short time behavior when this wave packet has still not seen the boundaries, right? So then it seems like infinite. So then you should just get back that. Okay, so just try to see that, and then at longer times it will look like this. I mean, it will look like, I mean, just one cosine thing will dominate the form. Okay, so so that's about this problem. Any questions? I won't go into details, but I just want to say a few things about higher dimensions. So, in basically, if you have like 2D or 3D or whatever lattice, in fact, as long as you have a regular lattice, doesn't matter. Okay, it can even be a honeycomb lattice or whatever lattice you want. You can always define the problem, and it's easy to do a lot of stuff. Okay, and so basically, again, you want to start from some point, let's say the origin, and you want to find what's the probability it's at some vector x bar. So, in general, in many dimensions, this is a x1, x2. So, it has xt components, and you want to know what is probability x bar, it's at n, right. So, you can always again write a master equation, and this equation is basically n plus 1 is equal to okay. So, it is basically so at each site you can gain from so if it is 2 dimensions 4 sites, if it is d dimensions is 2 to the power d sites. So, let us just consider cubic lattices. So, each site will have 2 to the power d neighbors, right, and so this is the probability of hopping. So, each site you can go into any of the 2 to the power d directions with probability 1 by t to the power d. Okay. So, this is the problem where you do not have a probability of staying at a site, you always hop to some site with this probability, and then you just see 2D, oh 2D, right, sorry, 2D, right, yeah. So, yeah, 6 kilo. Okay, and you can come from so P so let me, so in for you can just label like you have unit vectors E1 hat equal to 1 0 0 and E2 hat equals to 0 1 0 and so on. So, you have d unit vectors E1 hat to ED hat, which give you the direction, and so you can come from any of those positive directions, or you can come from n, and then you can go to any of those. So, that is minus okay. So, this is the loss term, right. Okay. So, this is basically I mean it is just a Laplacian generalized to like any dimensions. So, I mean this sorry, what was, no, this is not there, there's no, if you write rate equations, then there is a loss term. If you write just probabilities, then that is the only thing, right. Okay. So, now if you subtract minus p n, then you have this term. Okay. So, then you have this minus 2d p of n, and okay. So, this is basically I mean this is 1 by 2 d. Okay. So, this is the definition of the discrete Laplacian operator, and now again you can go to the continuum version and you just get okay. So, this is just the general Laplacian, and the good thing is that I mean even though this discrete, this equation is very hard to solve, and it's also, as I discussed, it's difficult to solve it combinatorially, but this one is always easy to solve, and the general solution is P of x bar t is just I mean it's like independent 1D walkers, and so the final solution is just 1 by, so you just write the solution 2 pi dt and raise it to the power d, and then it's some product of all the Gaussians. Okay, so it's minus okay, and here if you calculate what is x square, yeah, average. Okay, so this is so I use small x always for the continuum limit, right? Okay, so this is now just sum of x right. Okay, so now there is a factor of d here. If you look at r square, it goes as so in 2D it would be 4 dt, and 3D it would be 6 dt, and so on. Okay. What is the, so this is the original question that this guy Pearson had asked, right? What is the number of mosquitoes in this distance R2 R plus dr. So, from this how will you find that? Okay, so this thing gives me the probability of, if I have a small area element dx dy, then this times dx dy gives me the number of or probability of finding a particle in this volume. So, if I want probability in this volume, so that is what I wanted to find, right? This P, so let us just call it P tilde r dr. So, this is the number of mosquitoes in this volume. Okay. So, this is what I wanted to find. So, then what should this be equal to? If I know this, it should just be the area of this times this object, right? So, it should just be 2 pi r times p, which is this, and this if I write in terms of so it is 1 by okay, so root 4 pi dt, and d is 2, so that just becomes 4 pi dt, and it is e to the power minus r square by, okay, so that is equal to r by, okay. So, this is P of r. Okay, so here this one, if you plot, actually it's not, the maximum is not at r equal to 0, because, right, because you have so many guys out here. So, this one if you plot, it looks like I mean r starts from 0 and it's so linear, and then it has some here. So, this is P, okay. I am just calling P tilde. Okay, and this is actually the answer that this Rayleigh had given. I mean answering this question by Pearson. Okay. Okay, so sorry, diffusion constant is now d times 2d, and yeah, it's because d I am just defining as the thing, right? I mean, yeah, so this of yeah. That is still like here, if you look at see, because supposing I start from the discrete model, right, then of course this is I mean this is still true that this is the sum over xi I and if I do x square average, I will just get a square times what d d and n, and I will get if zeta L I say that it's plus 1 minus 1 and so like plus a minus a in all 6 directions, then zeta square average is what? Huh? Sorry, so I am saying zeta bar L is let's say a so plus minus zeta with probability 1 by 2d, right, with all possible. So if I take square, it's still 1 by 2d into 6 a square, right, or so it's still a square. So I still get a square dn, sorry, no d, sorry, just a square n. And then if I okay, so now if I define right, okay, so maybe the diffusion constant changes. So I put a tau here and a 2 tau here and 2 here. Then okay, so this if I call so let's just call it d bar. Okay, so then this and this are different, right? Yeah. Right, yeah, right, yeah, yeah. So this one has to be careful, like how exactly things are defined. Yeah. Okay, so usually when you write diffusion constant, I mean the equation should appear like this, and then of course microscopically you have to see what exactly it is. Okay, so okay, so I won't go much into like higher dimensions. I mean pretty much everything you do in 1 dimensions you can do in higher dimensions. Okay, so the next thing I want to talk a bit about is okay, is the following problem. Okay, so Sanjeev talked about this first passage thing, right? Huh? So what did he do? Like the probability that you arrive at A for the first time, and then did he do this in 1 dimension? 1 dimension, okay. And did he talk about Polya's theorem? Huh? No. Okay, so okay, so basically it's again the same question. Like so, the basic question is the following question. So basically, supposing you are okay, so you are located here, and then you start doing a random walk, right? And so one question: if you start doing a random, what is the probability that you will ever come back here? Okay. So this is I mean sometimes referred to as the drunken walker's problem. Okay. So basically you you go to a pub, okay, and then like drink a lot, and then you start walking randomly. What is the probability you will ever reach home? Okay. So so what do you think is the answer? I mean, of course, you might get run over, but assuming it's a perfect world and it's a lattice, I mean, maybe it's a lattice. Anyway, you take steps discretely, of course, right? So, so what is the probability you will ever reach home? And you can walk for infinite time, and also assume that the earth is infinite. I mean, it's like it's infinite, so you can keep walking very far. So what is the probability you will ever come back? Huh? 1, right? Okay. And if you are doing okay, so the answer is 1. So the answer is in 1 and 2 dimensions it's 1. In higher dimensions you may not come back. Okay, you might just keep wandering. Okay, so physically it's clear, because if you are if there's so much space, right? So there's more chance that you can just wander off and never come back. Okay, so so that's what we want to. So this is called usually called as the Polya problem. Okay, so Polya was a famous mathematician, and actually he has a very nice book which I strongly recommend. It's called How to Solve. I think How to Solve It, right? Anyone? Huh? Solve it, right? Yeah. Okay, so this is a very nice book where he just teaches various tricks of like solving problems without I mean like without going into and like doing things very simply, okay, and but getting the correct result. Okay.
So would it be true of any point
Huh?
Given some arbitrary point,
Huh.
you can ask the question, will you ever reach that point, right?
Oh, starting from here, can you reach some arbitrary point? Yeah, this also you can ask. This and this are almost the same. Okay, so if you know, if you return here with probability 1, you also return there. Go visit an arbitrary point, probability 1, right here. Okay, but we'll just anyway, so let's start with focusing on this question, probability of returning to 1. Okay. Okay, so for this first I'll sort of prove one result which is also kind of nice. So supposing so we define this object P x bar in any dimensions, and we said that basically, okay, so this is the probability that after n steps I am at x. Okay. Okay, so just to be clear, if I just put n equal to, so supposing so this is starting from origin, right? This, when I state this result, this is always starting from origin. This is the probability that I am at some point x after time n. Right now, what is the probability I am at? I am again at the origin. So that of course is just p of. So this is the probability that after n steps I am at the origin, right? So is this the probability that I ever come back? Because that's what I want to find, right? Starting from here, what's the probability I ever come back here? So from this, if I sum over, okay, so supposing I ask what is the probability I come back to this point after n steps. So then does this give me the answer? Okay, is the question clear? I start from here at time 0. I ask what is the probability that I come back here after n steps. So if I just put equal to 0, then does it give me the answer? Okay, so if I sum it over n, that probably gives me the probability I will ever come back. That's what you might think, right? Okay, but there is a problem here, because I come back here, but so when I look at paths which contribute to this, it also includes path which I already came back here. Okay, so it's not a first passage, right? So this one includes path which have actually come back before and then have again come back. Okay, so therefore it's not a first passage thing. Okay, so what I am interested in is a different quantity, is I'll call it f x bar n. So this is the probability that I come back to I go to x, or let's say the origin, for the first time in n step. Okay, so this if I take and sum over n, then I will get the probability of ever coming back. Okay, so this and these two objects are different. Okay, so that's why if I just put x equal to 0 and sum over n, I won't get the correct answer. Okay, so okay, so our objective is to try to find this. Okay, so let me just again explain what exactly I mean. So supposing I do a 4-step walk, right? So what is the probability that after 4 steps I can ask two questions. What is the probability after 4 steps I am here, and I can ask what's the probability after 4 steps I am here for the first time. Okay, so there are two different questions. So in the first question I will just look at, so what are the coming back here, what are the paths. So it will be like maybe this one, this is one possible path, but in this path, right, this is a path which will contribute to this probability that p 0 after 4 steps. Okay, so this is one path which will contribute to this probability, but in this path I have already come back once. Okay, but if I want this object, then I should only look at objects like paths like I start from here, go here, go here, go here, here. Okay, so it's so this path of course is the first time it's coming back, right? So when I compute this object, I should only sum paths like this. Okay, so therefore these two objects are different, and this and this. Okay, so that's why it's a bit tricky to find this, and we'll just discuss how to you can actually relate to these quantities. Okay, but so okay, so now supposing I look at this quantity p x bar n, infinity. Okay. Okay, so now what is this quantity? Okay, so this actually has a nice physical interpretation. Okay, so this basically gives me okay, so this basically tells me, supposing I do a simulation, okay, the walker starts from here and it keeps walking, right, and when you do the simulation, every time visits this site, you just count it, okay. So it does, I mean, and you let the walker walk for an infinite time, right, and it goes from 0 to infinite, okay, so and you just keep counting how many number of times it has visited this point, okay. So you will get some number and you do this many times and you get an average, right. Then this what you can show is that this is exactly this, okay. So it's just the mean number of times a given site is visited, okay. So so let me just explain why this is true. Okay, so what is P of x bar n? Okay, so P of x bar n is basically okay. So when you find this, supposing you supposing you are doing a simulation, okay, and you generate all possible paths of n steps, okay. So how many paths are there? Huh? How many n step paths are there? Okay, in 2D it's 4 to the power n, in 1D it's 2 to the power n, and in general dimensions it's 2D to the power n, right. This is the number of paths, okay. So supposing I do a simulation, I generate all these paths, and for each path I so this is the number of realizations, right. So this is in d equal to 1, d equal to 2, d, this is the number of possible realizations of the random walker, okay. And if I want to compute this in the simulation, what I will do is I will sum over all these realizations, right, and I will just see in at time n, right. So I generate walks of like let us say this is one possible realization, and at so this is n step walk. So at time n is the walker at x or not, right. If it is at x, then I count it, right, and I do it for in some realizations in at time n it may be somewhere else, right. At some in some realizations it would be at x, okay. So what I do is I basically put a Kronecker delta, and so a given path is like x bar L. So this is a path L equal to 1 to n. So huh? L levels the time, right. So L is 1 to n. So x1 is here, this is x bar 2, x bar 3 and so on, and this is x bar n, right. So x bar L is just the path, right, and if at x then I count it, right. So if I just do this counting and then I just divide by the total number of realizations, that should give me the probability, right. I mean, this is this clear? I mean, this is actually what you do in a simulation, right, and this is also an exact thing. Okay, so now I take this and okay, so I said x bar okay, so now I take this and I sum over n.
On the right hand side. So the summation is over n or no?
Oh, sorry. Sum over is different realizations.
Yeah. So R
Huh?
R is the
R is the number of realizations. Yeah, it's the sum over all possible realizations.
yes.
And at time n, I just see
Whether it's at x bar.
where this
So,
is.
it would be, I guess, more appropriate to label it as some, say, y. Then that would be like delta of y of kind of.
Which one? This one?
No, yeah, that. Y bar. And here summation over y bar. That's summation over all different ones.
This. Oh, so some R is possible paths, right? Yeah, yeah. Okay. Right. Yeah. So this is basically y bar n. All walks of size n. Right. Yeah. Okay. So now if I sum over x, I basically get and delta. Okay, so now I sum over n, and so then if you look at this object, okay, so what is it? I mean, it's basically in each realization, in a given realization, then it's okay. What am I saying? So this object is right. Okay, so and then I am averaging over all possible locations. So therefore, that's what I said. It's the mean number of visits to site X. Right. Okay. So that's okay. So the okay. So now I will use this fact to find this object. Okay. So I mean, right. Yeah. So we said that this P.
But there is, can you take the sum over n inside, because there is 1 over that r is, that is 1 over 2 to the t, 2d to the n, right? That 1 over r that you have written.
Right. Yeah. It's okay. Number of. Yeah. Initially, you have to do n a, and then you are doing a sum over the. I mean, see, okay. So supposing you do one realization, okay, of n steps, okay, and then you do another realization, and so on, and you do so many realizations. Okay, maybe we'll do this again in the tutorial. Okay. Huh? Okay, yeah, this is a bit subtle. I mean, let us discuss again in the tutorial. Okay. I mean, it's correct. I mean, you just have to write it carefully and just make sure it's okay. But it's correct. Okay, so we'll discuss this again in the tutorial. If you sum over x,
So this is equal to mean number of visits to site X.
this one.
No, you said that below. This is equal to mean number of visits to site X.
If you sum over x, of course, you will get infinity.
You get, let's say finite lattice, then it should be n, right?
finite lattice. Okay, okay. So first of all, if you take this and sum over x, it's 1.
Exactly. So
It's 1, and then if you
for each n, it will
sum
be 1.
for any n, then if you sum over n, it will be infinite.
Yeah, so if it's a finite lattice, it will be the size of the lattice.
Even if it's a finite lattice, it will be infinite, because at each time it's 1. Oh, if you are saying it, then of course for larger, no, for any n, it's always 1 and it's always infinite, right? Yeah, it's always infinite. Okay, so okay, so this one I'll just call it g of okay, so in okay, so in general instead of summing over n equal to 0, you can put something like z to the power n, okay, and define something like this. Okay, so this actually what you are doing is basically if you think of continuous time, then so there you do something like this, p of right. So this is what I mean, this is just a Laplace transform, right? So when I am doing it in discrete space, it's basically like a just a Laplace I mean like a discrete Laplace transform. Okay. It's also called a generating function. So in general, I can define this object. So now it's z, g of xz is 0, and g of x bar, if I put z equal to 1, then this I argued that this is the okay. So now what you can do is okay, so supposing I want to look at this 0 1, okay, mean number of visits to site 0 to the back to the origin, okay, so this is equal to, so now I'll try to say relate it to this okay, so so this is the probability that it will return to it will ever return to the origin, right? So this is okay. So now how do you relate it? So basically if you, I mean if you start from here, what can happen is that I mean there is a possibility that it will actually never come back to the origin, right? So that is one possibility, or it can happen that it comes back once and then it never comes back, right? Or it can happen that it comes back once, comes back twice, and then never comes back. Okay, so there are various possibilities. So in this case, if this happened, then it visits only once, right? The number of visits is 1. If this happens, then the number of visits is 2, because including the starting time. If this happens, the number of visits is 3. So therefore, I can write a formula for G, which is the mean number of visits, is equal to, so if this happens, so this is number of visit is 1, and what is the probability of this? What is the probability I never come back to the origin? Huh? It's 1 minus f, right? F is the probability I will come back, so it's 1 minus f. Plus, so then this is 2 visits, and what is the probability of this happening? Yeah, so I come back once and then I never come back, right? and then 3 is just f, I come back twice and then I never come back, and so on. So, this if you look at, you can just sum it up. So, it is 1 minus f and then 1 plus 2 f this, and this series you can find because 1 by 1 minus f is equal to 1. So, if you take it, so, okay, so this is, I am counting the mean number of visits, right. So, for this process the number of visit was 1, for this process it started and then it came back, so factor of 2, this one it came back twice, so factor of 3. So, that is for the factors, and so you basically have some series like that. So, next you will have f4 f cube and so on, and so you have so now how do you do this sum? If you take this is this, and if you take derivative you get 1 by 1 minus f square. So, that is this series. So, therefore, this is equal to okay. So, that is so therefore, G is equal to 1 by 1 minus f, and if I take here, so f is equal to okay. So, this is a very important result, and now so what we can find is actually G very easily. Okay. So, the reason is that okay. So, how do you find G? So, because so we wrote this equation for P equal to, okay. So, let us just do it in let us say 2D. This is x plus 1. Right, this is basically how P evolves in time, and now I just supposing I and that I also put delta x 0. So, at for delta n 0. Okay, so for time n equal to 0, it is the origin. Okay, so now if I take this and I do this that I multiply this by z to the power n. Then and sum over all n, then what I will get is basically so this is what z, and this one just gives plus delta. Okay, so if you put z equal to 1, then actually it's just like I mean it's basically like solving this. Okay, so it's just solving this equation, right? It's like electrostatic problem, like you have a charge at some point and you want to find the potential. Okay, so I'll just I mean this again you can just do a Fourier transform, right? If not Fourier transform, but a Fourier series, and solve this, right? So I'll just write the solution. Okay, and so if you do this, then what you get, so the final answer is G of okay, so this is the final answer. Okay, so this is just if you like normally you solve this equation by Fourier transform, you just do Fourier series and then you will get this. Okay, so this is also homework. Okay, so now what we want to show, what we started to ask the question is like we want to show that Polya's result. So we want really x equal to 0, right? Because this is for return to the origin. So so okay, so I should just write f of 0 bar. Okay, so this is what we want to show. Okay, so which means what? That in 1ND, what should this be? This should be infinite, right? So basically, okay, so now we have to just look at this integral and do it in various dimensions. Okay, and that will okay, so. So if you put x bar equal to 0, then this integral is just so in one dimension. So that object is 1 by z01 is equal to okay, so this is infinite, right? So why is it infinite? How do you see it's infinite? Huh? What? Singularity at theta equal to 0. So at small theta, but that's true for all of this, right? So how do you now find out whether it's infinite or finite, right? All of them have a problem. If you put theta equal to 0, this denominator is always infinite, right? But if it is infinite, it can still be finite, right? So how do you find out? So you basically you look at the small theta behavior, right? If like I mean this integral x to the power x square, this will diverge, right, 0 to let us say 1, this will diverge because, but if you have something like x to the power half, even though at x equal to 0 it is infinity, when you integrate you get x to the power half, so that does not diverge, right. So, this is a finite integral, and so basically you have to see the nature of this guy at small theta, right. So, in 1D, I mean if you expand near small theta, so this is because this is diverging, we just want to see nature at small theta. So, it is 1 by theta square, and then clearly this is 1 by theta, and so at theta going to 0 it blows up, right. So, this is infinite. Okay, then in 2D if you do this, so then you get d theta 1, d theta 2, and again you look near theta equal to 0. So, if you are looking around the region, then you can just go to polar. So, this becomes like theta 1 square plus theta 2 square, right, and then you can just go to polar coordinates. If you write in polar coordinates this integral, then this becomes d theta by theta square, right, near small theta. So, now again this one is 1 by theta, and so that is log theta, which again diverges at small theta, right. So, this in 2D, so this is d equal to 2, so this also goes to infinite. Okay, and then if you do 3D, then what you see is basically you will get in general arbitrary dimensions. If you look at small theta, you will basically get something like theta to the power d minus 1 by theta square. Yeah, and this of course if it is 3, it's this cancels and there is no divergence, right. So, therefore, this d to the power d is not in 2 . And you can actually like some of this I think maybe some of these numbers are known exactly, okay, like you can do the integrals in 3 and maybe 4 dimensions. So, they are complicated integrals, but you can somehow do them, and so so you get some exact number, like I think in 3D it is maybe probability of ever returning is like 0.6 or something, okay, and if you go to higher and higher dimensions it goes to 0 in some way. Okay, so that is the basic this Polya's theorem, and if you, so here I set this equal to 1. So, in general what you can do is you can actually relate z. So, you can actually relate these two objects, and this is easy to find, and then you can find this, and then if you take an inverse Laplace transform, you can find f of x t. Okay, so that is one like standard way to find the first passage time distribution, and this is particularly useful for like discrete problems. Okay, so okay, so in the tutorial we will just go through that argument again. Okay, so that is actually quite a bit tricky, and every time I do it I get confused, but it is good to I mean just write it down carefully, then you see it is okay. Okay, so we